grade, that stuff. Okay. All right, here we go. So we're going to start on that notes packet. Some things are I just put enough information on there that someone that couldn't come to class would survive, okay? So if you feel like I'm reading it to you, I apologize. I don't do note guides very often because I don't really like it when people read me things that I have right in front of me. But I feel like I have to say it anyway, so here we go. So the chance or probability of something gives the percent of time it is expected to happen when the basic process is done over and over again, okay? So when I say that the likelihood of getting an A in this class is 80%, that number is coming because over and over and over again, I have given students grades for this class, and it seems like about 80 out of every 100 grades is the letter A, okay? But it's after over and over and over again. It's not after 10, right? After 10 grades, if there are 8 A's and 2 other grades, it's not. It's a process that has been repeated. Sorry, I got it tickled. Over and over and over again, okay? When you think of a process that is done over and over and over again, there are a few that come to mind quite frequently, and those would be like flipping a coin or rolling a die, okay? So a few probabilities are written out there just so you can start to get used to the notation. When I write something like this, when I write that, how do I actually read that? What is that saying? P parenthesis heads parenthesis. What, how do I actually say it? Any ideas? Yeah, this is the probability that you'll get a heads. Okay? Does everybody feel confident in that answer being 50%? Yeah? Does everybody also feel good with the fact that we could actually say it's 1/2? Okay, technically, I didn't put it on here, but technically we could also write it as 0.5. Not as common, especially in this book, but that is a possibility. Okay? The probability of rolling an even when you roll a die. How many even numbers are there on that 6-sided cube? There's a 2, there's a 4, and there's a 6. So how many of them are even? 3, so that's how many I want, right? That would be considered a success if I'm counting the number of evens. So 3 of them would be considered a success, or what I want, out of 6 possible faces that could be showing from that die. So we usually write that just as, again, 1/2 or 50%. Good? Okay. All right, so let's just do the first example. And these ones I actually want you to fill in on your notes as we go. So the first example says that box A contains 3 red marbles and 2 blue marbles. So in a box, we have 3 red marbles and 2 blue marbles. In box B, if I don't want to write out this, they do this quite a bit in your book, so I'm just going to warn you up front. In box B, there's going to be 30 reds. I don't really want to write R 30 times. So I can go like this. Okay? And then there are going to be 20 blues. So 2 different boxes. You're going to win $5 if you draw a red marble. Okay? If you stick your hand into one of these boxes and you are able to pull out a red marble, you win $5. If you pull out a blue, you don't win anything. So this is just a personal question for each of you. Which box would you rather be drawing out of? Box 1 or box 2? Why? So that you had to pick up the heavier box and carry it over there? Yeah, because there's more reds. Is it too loud? I can talk louder if you want me to. What's up? Can you still hear me? Did I turn it off? No. Back? Yes? Okay. What'd you decide? Which box? Just because there's more reds, yeah? The catch with the more reds is that there are also more blues, right? That's dangerous. So some people might say, I want box 1 because there's only 2 blues that I have to avoid. It's a tie. It is. And I think you know that going into it, but then when I make you think about it, you second guess yourselves a little bit. Okay? So we could say for both of these, the probability of red is what? Yeah. You could say it's 3 out of 5. That would be the easy way to say it, right? Because there are 3 successes. There are 3 reds out of a total of 5 marbles. Or we could say 60%. Yeah. Either answer is perfectly acceptable. It doesn't matter to me which format you put those in. Not on this assignment. Maybe later, but only when we're doing stuff that can't really be described this way. So either way, the probability of pulling a red is 60%, so it does not matter which box we choose from. Okay, so a couple of phrases. Why is there a random space right there? It's fine. So the key phrase, with replacement. If you draw a card or a ticket or a marble, whatever it is that you're drawing out of a box or a bowl or whatever, and then you put it back before the next draw, okay, then you are drawing with replacement. Without replacement, what? You just keep it, okay? So a lot of times we talk about cards, like playing cards. If I'm dealing cards, am I replacing? No, I don't show you that you got an ace and then put it back in the deck and then give you your next card and then put it back in the deck and then get, right? That makes sense, okay? When you go to, like, you know how sometimes you go places and you have those little tickets and they, like a raffle type thing, and they call out the numbers? After you win a prize because they called your ticket, do they put your ticket back in the bowl? No, because then you could win everything, and that's not good. Right? Okay. So with replacement, without replacement. What? Sorry. Okay, and then the other phrase that your book likes to use a lot is the phrase draw at random. All that means is all the items that are being quote unquote drawn have the same chance of being picked. Okay? Like with those marbles, there isn't a difference between the texture of the red marble and the texture of the blue marble. Everything is the same. When we talk about the tickets are all going to be the same size, all the same type of paper, all the same, yeah, same weight, same everything, okay? My husband likes to play this game with our kids. My husband works at a bank, and so occasionally he'll come home from work and he'll have a bunch of cash just for whatever reason. If we're going to go make a big purchase and we needed cash for it, or we're getting ready to go Christmas shopping and decided to use cash this year, whatever it is. So he'll come home and he'll have like some $100 bills and some 50s and some 20s and some 5s and some 1s, just like a random assortment of dollars. And he will like fan them out. He'll like mix them all up, make the kids close their eyes, fan them out, and they can pick one. And the rule is if you get over $20, you get to keep it. Yeah, but guess what? He never loses. Ever. And I don't understand. Even me. Like, I'm baffled by it because you like go and you can feel, and usually the hundreds are the newest, like they're so pristine, like untouched by human hands. And you would think I would be able to like feel that. Like there's gross $1 bills, right? And you can tell that they have been through a few gas stations and possibly some casinos and maybe some stripper clubs and right? Like they are just gross, or they've been shoved in some little boy's pocket and washed and dried and washed and dried and yeah. Sorry. Anyway, so like you would think I would be able to feel the difference, and honestly, I always pick like a $1 bill or maybe a $5 bill, even after and a huge part of it for my kids is that they're just not patient. So they just reach and grab, and whatever they grab first, they just go for it. But I've tried to learn to be so patient and like really like feel them and try so hard to find the hundreds, and I can't do it. Anyway, it's a sad story. And I watch, like it's not like he's showing them and all the hundreds and fifties are in there, and then he somehow like pulls those out when they actually draw. No, they're right there. I'm watching the whole time and I'm like, how is this happening? Anyway, dumb little side note. Okay, so drawing at random, you just have to make sure there isn't a reason why one draw is more likely than another. Okay, it's usually just a given for us. Okay, the next thing we're going to talk about is conditional probabilities. Conditional probabilities are calculations involving two events, but we're only calculating the likelihood of the second event with the understanding that the first event already happened. Okay? So, a conditional event could be something as simple as, what's the likelihood of flipping a heads, given that the first time you flipped the coin, you got a heads? Okay? So let's look at that. So if we have conditional probabilities, right? Sometimes they don't, sometimes they will. So conditional probabilities, if I said, what is the probability of a head given, that vertical line right there says given, I already flipped a heads. Does that given information actually change what happens here? No, it's kind of like with replacement. I got a heads, but I put the head back on the coin and then let you flip again. Does that kind of, sort of? Yeah? It's automatically like a with replacement. So this condition doesn't really impact anything, so my probability is still 1/2 or 50%. Okay? What's the probability? We're going to talk cards quite a bit while you're here, because a lot of you don't really understand playing cards very well, and I hate to leave you on your own to do your assignment that is all about playing cards when we haven't discussed. So, what is the probability of drawing a heart given that your first draw was a diamond? So we're drawing twice, 2 cards. Okay? Now, those of you that aren't familiar with a deck of cards, there are 52 cards in a deck. Let's just write this out. It says it in your book. So there are 52 cards total. Okay? There are 13 hearts. What else? 13 diamonds. What else? Okay, why are there 13? Do you know what the cards are? Okay, so there's an ace. Then what? 2, 3, 9, 10. Then what? A jack, a queen, and a king. So those are the 13 cards that you have in hearts. You have them again in diamonds. You have them in spades. You have them in clubs. The only other thing you need to know is red and black. What are red? Which ones? Yeah, hearts and diamonds. All 26 of those cards are going to be red. All the spades and clubs are black. Okay? So that question that I just asked you, that conditional probability of what is the probability of choosing a heart, given that your first card was a diamond, you actually don't have enough information to answer that question yet. Does anybody know what additional information I need? Yeah. So the question that I still need answered here is, was this done with replacement or without replacement? So let's try it first with replacement. So if I draw a card, if I shuffle a deck of cards really well and I draw off the top and it's a heart. Nope, I lied. It's a diamond. First one was a diamond. And then I replace it, shuffle the cards again, and draw, and I get a heart. What is the likelihood of that heart? Well, how many hearts are there? 13. Out of how many cards total? 52. Another way to look at it is because hearts are 1 out of 4 of the different, what are they called? Suits. Thank you. So hearts are 1 out of 4 suits. So 13 out of 52 is the same as 1/4. You could simplify that fraction, or you could leave it. Okay? So this is 13 out of 52, or 1/4, or if you really wanted to put that as 25%, that's totally fine. Does your family play cards? My kids know all that stuff too. We play lots of cards. Okay, now what if I don't replace? What is the probability of a heart given that my first draw was a diamond? No. This was just kind of go through and get comfortable with it. So the probability of a heart given that I already drew a diamond. So I shuffle, I pull a diamond, I keep it in my hand, I draw again. What is the likelihood that that second draw is a heart? There you go. There are still 13 hearts in that deck, but there are only 51 cards in that deck. Yeah? So a conditional probability is just saying you have to think about what happened before in order to calculate what's happening now. If you had to, it would be in your calculator. But no, especially on a problem like this, I would never. I promise. Okay. All right, so go ahead and do the example at the bottom of that front page. So it says a deck of cards is shuffled and the top 2 cards are put on the table face down. You win $1 if the second card is the Queen of Hearts. Okay, so I drew out 2 cards. There's card 1, there's card 2. What is your chance that that second card is the Queen of Hearts? Is this an example of a conditional probability? So my 2 cards, I'm just going to actually grab some cards. Hold on. So if I have my 2 cards, okay. 1, 2. Okay, the first question just asks, what is the likelihood that this second card is the Queen of Hearts? It is 1 out of 52. Why? Because there are 52 cards that could have ended up in this spot. Now, we understand that we took another card out first. But because we don't know what it is, this is not a conditional probability. It is just the probability that that card is the Queen of Hearts, and because there are one Queen of Hearts. Because there is one Queen of Hearts that it could possibly be out of all 52 cards, the likelihood is 1 out of 52. Now, in reality, did I get a Queen of Hearts? That would have been cool if I did, though, right? Would not have been so cool. Okay, didn't happen. Okay, next question, though. If the first card is turned over and reveals itself as the 7 of clubs, what is the likelihood that the second card is the Queen of Hearts? No, but still sitting there. So I deal those, turn this over, and it happens to be, not the Queen of Diamonds, it happens to be the 7 of clubs. What is the likelihood that this card is the Queen of Hearts? Now it's 1 out of 51. Do you understand why? Because now I know for sure that one of my 52 cards is not here. Yeah? Kind of, sort of? Okay. All right, page 2 of the note guide. Here we go. That one just shows you the notation. I've already kind of used the notation, so go ahead and just transfer your answers. So the probability of winning the dollar was 1 out of 52. The second one, the probability of winning the dollar, knowing that that first card was a 7 of clubs, was 1 out of 51. Good? Okay. The next thing we're going to cover is what we call the multiplication rule. The multiplication rule states that the chance that two things will both happen equals the chance that the first will happen multiplied by the chance that the second will happen, given that the first already happened. Okay? So we have to, when we use the multiplication rule, we have to be careful and watch out for those conditional probabilities. So, our examples. 2 cards dealt off the top of a deck again. Okay, what is the probability that the first card, so we want the probability that the first card is the 7 of clubs, and that the second card is the Queen of Hearts. Okay, careful. I know what you just did there, so be careful. So we're going to multiply. Okay, what is the likelihood of the first event? It's the likelihood of getting the 7 of clubs. How many 7 of clubs are there? Just 1. So there's 1 out of 52. Okay? And then the second card needs to be the Queen of Hearts. How many of those are there? 1. What is the likelihood of getting a Queen of Hearts if I already have the 7 of clubs? 1 out of 51. And what do I do? What did the rule say to do with these two numbers? Multiply them. How do we multiply fractions? You get out a calculator. You go straight across. Okay, so it's 1 times 1 is 1. And then on the bottom, I'm actually okay, just so you guys know, moving forward, this is perfectly acceptable. If you don't have a calculator with you, you are more than welcome to leave your answer as 52 times 51 in the bottom. If you multiply it out, you get...
That's not very likely.
It gets worse.
I feel like
Okay? So there is a 1 in 2,652 chances. There's a chance of one time out of all of those draws that we would get the 7 of clubs and then the Queen of Hearts. Because that's super, super specific. Okay? All right. What is the chance that both cards are aces? So part B. So what is the chance? So what is the probability of an ace and another ace? Two aces in a row. So how many aces are there? There's an ace of hearts, an ace of diamonds, an ace of spades, and an ace of clubs. Agreed? So how many aces total? Out of how many cards? 52. Or we could think of it as every suit has an ace. Yeah? So 4 out of 52 is going to be the same thing as 1 out of 13. If you just simplify the fraction. Okay? So this first ace, flipping that first card over and having it be an ace, there is a 1 in 13 chance of that happening. But be careful. When you read the multiplication rule, it says it will be the chance that the first will happen multiplied by the chance that the second will happen, given that the first already happened. So what's the likelihood of this ace? 3 out of 51. Do you know where those numbers came from? How many aces are left if this one was successfully an ace? 3. And how many cards are left? 51. And what do we do with those two numbers? Multiply. So we multiply straight across. We get a 3. And then we can write 13 times 51. Or somebody can throw that in a calculator for us, and we get, what is it? 663? Oh, so we could actually simplify that then. 1 out of 221. All right. So which is more likely? 7 of clubs, queen of hearts, or 2 aces in a row? 2 aces, because it's slightly less specific. Yeah, it would have been the same if I would have said it had to be an ace of hearts and then an ace of diamonds. We would have had the same probability. Okay, good. The next example. This time we're tossing a coin. Change of pace for a second. Tossing a coin. What is the chance of flipping a head and then getting a tail the next time? So probability of a head and then a tail. What's the likelihood of getting heads? Like 1/2? Oh, these people cannot even see the board. Where's my... Oh, I just have it zoomed in too far. Move. There we go. Okay. So what is the probability of that heads on the first coin toss? 1/2. Then I already got a heads, so does that remove the heads from the coin? No. You pick that coin back up and you still have a 50% chance of getting a heads or a tails. So the likelihood of the tails on the second toss is 1/2. Multiply those together. How often would we get a heads and then a tails? 1/4 of the time, or 25% of the time. Good? Just as kind of a preview, there's a section on the next page where it talks about this, but just kind of as a preview, sometimes what you want to do is you want to make a visual representation of all the things that could happen. If you're tossing a coin twice, you could get heads and then heads, right? Or tails and then tails. Or you could get a heads and then a tails. Or a tails and then a heads. And would you say that all 4 of those have the same chance of happening? Yeah. So heads and then tails is 1 of those 4 options. So the likelihood is 1 in 4. So far, so good? Okay. What is the next question? What is the probability of 2 heads in a row? Same thing. Yep. Okay, read me what's next on your notes. After that example. What is it? Okay. Perfect. Okay, what did we just do? These events that we just barely did with flipping the coin, did the second event depend on what happened the first time? Did the chance of this tails change knowing that we got heads the first time? No. So you're saying this number would have been the same whether this was a heads or a tails, correct? Okay. So these 2 events are independent of each other. Okay? Look at this one. 2 events. Draw a card, then don't replace it, then draw another card. Are these 2 events independent of each other? Is this event dependent upon what happened here? Yes, so these ones are called dependent events. Okay? This second probability changed based on what happened in that first calculation. Yeah? Do you see the difference? Okay. So, toss a coin twice. If the coin lands head, on the second toss, you win $1. So, if the first toss is heads, what is your chance of winning the $1? So remember, you win the $1 if you get heads on the second toss. So if the first toss is heads, still 1/2, right? It doesn't really matter. So your chance, or your probability of winning, is still 50%. Okay. Now they are looking at the back table. I don't know why it goes so fast. Oh my gosh. I shouldn't have even touched it.
Wait, are they watching it right now?
Yeah. Sorry, guys. Just a little drunk with the camera. It's fine. There we go. Okay. Wow, that was difficult. All right, so toss the coin. If the coin lands on heads, you win $1. Oh, on the second toss. That's right. Okay. So if the first toss is a heads, what's your chance of winning the $1? 50%. If the first toss is tails, what's the chance of winning the $1? 50%. Are the 2 tosses independent of one another? Yes. Because what happens on the second event didn't change when the result of the first event did change. Yeah? So if sometimes you'll see this. Let me show you. So the probability of, let's just write it this way. Probability of heads on the second toss. Okay, so we look at 2 things. We look at what is the probability of heads given that we got heads, right? That was question or part A. Probability of getting heads, given that we already got heads, 50%. Probability of heads, given that we already got tails, was 50%. The fact that these two match tells me that these two events, the tossing the coin the first time and tossing the coin the second time, are independent of each other. And therefore, this answer is whatever we got there. Okay? Because those were both the same, that is the answer. It doesn't really matter what happened the first time. Cool? Okay. Next example. We're on the next page, right? Page 3. Okay, so top of the third page says 2 draws will be made at random from that box with the tickets 1, 1, 2, 2, and 3. Okay? So we have a box. And inside that box, we have a 1, a 1, a 2, a 2, and a 3. Okay, this time we're drawing with replacement, which means what? I draw a ticket, I put it back before I draw again. So there are always going to be 5 tickets when I draw. Okay? So it says, suppose the first draw is a 1. What is the chance of getting a 2 on the second draw? So this is, what is the probability of getting a 2 given that the first draw was a 1 and this one is with replacement? Two out of 5? That makes sense to everybody. So I drew a 1, I looked at it, saw that it was a 1, I put it back in, shake up the box, pull again. The likelihood of getting a 2 is 2 out of 5. Okay? Suppose the first draw is a 2. What is the chance of getting a 2? Still the same. 2 out of 5. Are the draws independent? Yes. Okay, now same box, same tickets, 1, 1, 2, 2, and 3. This time without replacement. Okay, so suppose the first draw was a 1. What is the chance of getting a 2? So if I draw the 1, there are now only 4 tickets. The likelihood of drawing a 2 is, yeah, you could write it as 2 out of 4 or 1/2, either way. Next, suppose the first draw is a 2. What's the likelihood of drawing a 2? So I pull out that 2. It's gone now. Now how many 2s are there? 1 out of how many tickets? Okay, both times we were asking for the likelihood of drawing a 2. Yeah? And we ended up with 2 different probabilities. So the question is, are the draws independent? No. These draws are dependent upon one another. Why? It changes the box. Whatever happens on the first one changes the box for the second draw if we're drawing without replacement. Okay? So drawing with replacement is kind of like our flipping of the coin. We're always putting the heads and tails back on the coin before we flip it again. So they're all going to be independent of each other. It doesn't matter. I mean, it's hard to wrap your head around it, but if you flip a coin 10 times and the first 9 times are all heads, does that mean you have a super, super high likelihood of getting tails on that 10th one? No, you still have a 50% chance, unless, of course, there's something wrong with the coin. But if it's a fair coin and you just luck of the draw, the first 9 in a row were all heads, that does not change the likelihood of getting heads or tails on that 10th flip. Doesn't matter. It's hard to wrap your head around. Do you ever like have a bunch of bad days in a row and you're like, oh, I'm due for a good day. Come on. Due for some good news. It doesn't work. I mean, you got to make your own good news, first of all, when we're talking about like real life and reality. But it's kind of that same thing. You know, my kids used to, when they were younger, they always wanted to play that stupid claw machine. Oh my gosh. The death of any parent, because you know you're just going to keep putting money in and nothing's ever going to change. So the first 5 times when we don't win, let's play one more time, Mom. Guys, our chances of winning are still 0. It doesn't matter that we've already lost 5. That doesn't increase the odds that we're going to win this time. We still can't beat this stupid machine. Okay? All right, moving on. Okay, when drawing at random with replacement, the draws are independent. When without replacement, the draws are dependent. Okay, moral of that story right there. Next examples. Do you guys want to try? Actually, no, we'll just do them together. So a box has 3 tickets. Yeah, this will be our last thing that we do for today. A box has 3 tickets. They are colored red, blue, and white. 2 tickets will be drawn at random with replacement. What is the probability of drawing the red ticket, then white? Is this asking us for the probability of just one event or the probability of 2 events? This one is asking 2. If they don't use the word given, then you are actually calculating both of these probabilities. Okay? It's kind of like saying, I want red and then I want white. Okay? You're going to learn that this is going to be our keyword that's going to tell us to multiply. Anytime a probability has the word and in it, it's a dead giveaway. You've got multiplication coming. Okay? Or if it says, like, probability of both aces, that means an ace and an ace. So that would be this case also. Okay? So it says a box has 3 tickets. 2 tickets will be drawn at random with replacement. What is the probability of drawing the red? Yeah, so it says, what is the probability of drawing the red? So what is that? 1/3. And then am I putting this ticket back in the box? Yes, it says with replacement. So now what is the likelihood of getting the white? Also 1 out of 3. So what's the likelihood that this entire event just happened? I multiply those and I get 1 out of 9. Yeah? Okay, next one. Nope, I lied. It says there's a special case of the multiplication rule, which says that if 2 things are independent, how did we know that these 2 events were independent? What made them independent? Replacement. I put the red back before I drew the white. Yeah? If 2 things are independent, the chance that both will happen is just the product of their probabilities. You don't have to consider the conditional. Like, I didn't have to really look at this one and go, okay, this one's got to be the probability of white given that I already drew red. It doesn't matter. It's just the probability of white because those events are independent of each other. Good? Okay. So that is the first half of your probability unit. So now I want you guys to work on homework number 16, the pink one. Okay? The second half of your probability unit will be recorded and posted for you. So you can either watch it on, I don't even know what day. It's all a blur. Monday? Monday I would have this class, yes? So you can live stream. You can hop in the Zoom room and live stream with us and watch it on Monday. Or you can watch the recorded video of it after Monday. That will help you finish your note guide and then be able to do the gold worksheet. So today you have so far learned everything you need in order to do the pink worksheet. So go ahead and work on that for about 15 minutes, I guess.